Well, good morning. Welcome to the Harmful Algal Bloom webinar series. My name is Laura Freskin, and I'm from the Iowa Water Center, located at Iowa State University, and I'll be your moderator today. Okay, this webinar is hosted by the Algal Bloom Action Team, of which Iowa State is a member. The Algal Bloom Action Team is a collaboration of water professionals, researchers, and educators from 12 states in the north central region of the United States. Team members include the National Network of Water Resources Research Institutes, the North Central Region Water Network, and the University Extension within each state in the North Central region. In addition to hosting a webinar series, our team has developed a website of resources, including fact sheets and frequently asked questions on HABS topics. I encourage each of you to visit our website, and I will put that in the chat in a little bit. There you can explore some of the resources we have to date, including a What You Should Know fact sheet, a HABS frequently asked questions database, and recordings from previous webinars and our virtual HABS Research Symposium, which we hold at the beginning of each year. Before we get started, just a few housekeeping items. We will have a Q&A session after Grace speaks today. So please list your questions and identify, please list them in the Q&A panel, and I'm going to try to address all of your questions following the presentation. If the question that you have is already posted and you have the same one, you can upvote the question so that I know that there's a lot of interest in that one, and we'll make sure to get to those. So today's webinar is being recorded and will be posted to the Algal Bloom Action Team website following today's session. If you have any technical issues or have any questions about the Algal Bloom Action Team, please list those in the chat as well, and we will be happy to assist you as best we can. So today's presentation is titled Short-Term Dynamics and Long-Term Trajectories of Algal Blooms in Lakes. Our presenter today is Dr. Grace Wilkinson from the University of Wisconsin-Madison. Grace is an associate professor at the Center for Limnology at the University of Wisconsin-Madison. She is a limnologist and ecosystem ecologist with a research focus on aquatic terrestrial linkages. Specifically, Grace's group is interested in the consequences of dynamic watershed inputs on water quality, nutrient cycling, and ecosystem resilience. Her group uses a combination of whole ecosystem experiments, long-term data, and high-frequency sensors to investigate patterns of and controls on lake dynamics. So with that, I would like to turn it over to Grace, and I will stop sharing my screen.
Thank you so much, Laura. And I'm going to share here. And Laura, can you just verbally confirm for me that you all are seeing my screen?
Confirmed. Looks good.
Awesome. Thank you so much. Wonderful. Well, thank you so much for the opportunity to be presenting some of my group's recent research on harmful algal blooms. And I really appreciate the opportunity to speak to this group. And so I'm going to share a couple of stories today about our research that really have to do with harmful algal blooms at various timescales. So really thinking about their longer term trajectories and how those have been changing over the past decades, as well as on the shorter term and thinking about prediction. Now, it seems like wherever we look these days in the news, we're seeing more and more instances of harmful algal blooms and the consequences that they have for these ecosystems and the people that are trying to use them, right? And as someone who really loves and enjoys lakes, of course, this makes me really sad. I really enjoy being able to go with my family to a lake, bring my dog, go swimming. And of course, we know, blooms really get in the way of this. But as a limnologist, when I see this, and it seems that more and more we're hearing about these harmful algal blooms, I start to wonder if there's perhaps something else going on. And so, as I mentioned before, and this is certainly not a group that is unfamiliar with this idea, but algal blooms are negatively affecting ecosystem services in the lakes in which they're happening. right? So we see consequences such as interruption in water supply due to cyanotoxins or taste and odor compounds that are being produced. It can also interrupt food supplies, particularly for people that are relying on that ecosystem for subsistence, both through the form of fish kills as well as potentially cyanotoxin exposures. And then, as I mentioned as well, recreators like myself, cyanotoxins can lead to beach closures, and they just overall blooms decrease the perceived value that recreators have of that ecosystem for going and spending their time and money in that place. There's also negative consequences for biodiversity and things like fish kills, as well as food web collapse. And homeowners around lakes that have harmful algal blooms regularly see a decrease in their property value. And so all of these combined consequences on ecosystem services affect the overall or create overall economic loss because of these blooms. So given, of course, the consequences of harmful algal blooms, we'd like to be able to prevent them from happening, predict their magnitude, and perhaps mitigate their severity. But we, of course, all well know that this is often easier said than done. And so what I'm going to share with you today are 3 stories from work that my group has either recently done, is currently in the hopper, and is coming out soon, as well as how some of our past work is informing future whole ecosystem experiments that we're going to be doing. And so these 3 questions are ones that I hope to address today. So first, thinking about long-term trends and whether or not what evidence we have if recently in the past couple decades, algal blooms are getting worse, quote unquote, in lakes. And then for some lakes where we know blooms are producing toxins, can we use that information in that toxin monitoring to create statistical models? And how useful are those models for predicting toxic lakes into the future? So what's the utility of those models? And then finally, thinking about short-term dynamics. Can we use the short-term day-to-day variability in what we're observing in the lake to predict before a bloom happens? And that's really a product of the resilience of the ecosystem. And so if we can measure that resilience, can we also find ways to enhance it? And so I'm going to start with this long-term trends. And of course, just to sort of create some context around this entire discussion, but for this group, you all are very well aware of you need lots of ingredients in order for an algal bloom to form. And it's the sort of complex interaction of all of these various ingredients that can make it really difficult to predict when and where a bloom might happen. Of course, one of the most important, you need light for photosynthesis and heat. Cyanobacteria, as well as other phytoplankton, grow more when it's warm, right? We, of course, need nutrients that are coming from the watershed, and the land use within that watershed, as well as human activities, are really going to influence the magnitude, so the quantities, as well as the ratio of nutrients coming off of that landscape. And it matters, for example, if there's other primary producers around for competition for those resources, things like light as well as the nutrients. And some nutrients will feed those algal blooms. They also can be stored in the sediments. And then we have legacy recycling of those legacy nutrients, particularly phosphorus, up into the water. And ecosystem properties such as stratification, as well as invasive species like the common carp you see pictured there, can really influence things like that nutrient loading. Other organisms, such as grazers in the lake, can help control some of that algal biomass. And so where their populations are at and how efficiently they're consuming algae and what's there can really make a difference. And also just how long these nutrients are sticking around, or the residence time within the water column. So these complex interactions of external and internal environmental drivers are what can lead to blooms. And as we very well know, human activities are causing large-scale changes in these drivers. So just giving 2 examples of some of those large-scale changes and sticking with the United States for those examples, but these are happening globally. We know that nutrient additions to the landscape and in the terrestrial environment have been widespread, and this is causing widespread eutrophication. So what I'm showing here on the left is work by Sebo and colleagues. This is a phosphorus inventory for the United States from the years 2002 to 2012. And as you can see, there are a lot of phosphorus inputs that are occurring on this landscape. And of course, here in the north central region, we see really high phosphorus inputs, particularly supporting the large agricultural industry that we have in this area. And those aren't just solely agriculturally related phosphorus inputs, although about 43% is coming from fertilizer and pesticides, and another 47% from livestock waste. But human waste also adding phosphorus into that terrestrial environment, and of course, atmospheric deposition. But as you can see, there's these large amounts of phosphorus inputs, which then of course lead to, when there's runoff, large phosphorus inputs into our surface waters. And that runoff is also changing. So across the United States and globally, there are regions where we're seeing precipitation intensify. And again, here in the upper Midwest and the North Central region is no exception, right? We are seeing more just an increase in precipitation as a total, as you can see on this map here. So the percent change in precipitation is being shown. And right in this area where we're adding a lot of phosphorus to the terrestrial environment, we have a lot more precipitation that's been occurring over the past century. And it's not just that it's more precipitation, it's more extreme events. And so the number of extreme events has also increased substantially, particularly over the past 30 to 40 years. So a lot of that phosphorus moving from the landscape and into our waters. And so given this, the fact that we're seeing this broad scale land use change and fertilization, intensifying precipitation, moving those nutrients off the landscape into the water, a warming atmosphere because of climate change. This is influencing things like stratification and the dynamics of how legacy nutrients are being released or are available for supporting algal blooms. All of these changes together means that it's a reasonable hypothesis that blooms are getting worse, that they would be getting worse in lakes pretty much widespread or everywhere. And so coincident with this algal bloom intensification hypothesis has been increased media attention, as well as a growing public awareness of algal blooms. So for example, in this map that's animating through here from the Environmental Working Group, each dot is a local news report of an algal bloom between 2010 and 2020. And during that decade, you can see the dots are building up. So it's not more each year necessarily, it's just the dots are remaining. And so it's this match of scientific anticipation and public attention, right? So the two combined, that's created the perception, broadly speaking, that blooms may be intensifying in inland waters. But it actually remains unclear on whether or not they are in fact getting worse. And so it's this simple question, are algal blooms getting worse, that my collaborators and I set out to address. In trying to understand over the past couple of decades, have blooms been getting worse in inland waters? Well, the first thing we needed to do is we needed to define what we meant by worse. And so we came up with 3 metrics for that. First is magnitude. So whether or not the average bloom is getting worse from year to year. So in other words, perhaps the bloom just used to be a pretty low amount of biomass, but it's now getting a higher and higher magnitude. So on average, the lakes are getting greener. And if we were to think about what that means in terms of ecosystem services, that could be correlated with an increased likelihood that ecosystem services that we rely on for that water body will be lost. There's also bloom severity. So if the peak of the bloom is getting worse, perhaps in the past, the bloom was pretty small. It turned the lake just kind of green like you're seeing in this image here on the left. But now when it blooms, it is scummy and pea soup and green, right? And these increased severity might be associated with an increased likelihood of severe consequences, things like fish kills happening in the system. And finally, thinking about bloom duration. So is it lasting longer and longer each year? And if that's the case, then it's going to become less viable or a desirable system for people to want to come and spend their time recreating on it. And so this could coincide with an increased period of summertime economic loss. So these 3 metrics, magnitude, severity, and duration, and how they're changing, is how we wanted to define whether or not blooms are getting worse, looking at these 3 components. And then next, we needed a way of actually measuring the bloom. And there's lots of different ways to do this. And each one of them has some benefits as well as potentially some flaws. And so the one that we decided to go with was using chlorophyll A concentrations in the water. And so these were from values that had been measured in the water. So samples taken by monitoring programs, volunteer programs, where that water had been collected, brought back to the lab, and the chlorophyll extracted and measured. And chlorophyll A is a common way it's a common index of algal biomass. It is certainly an imperfect index. We know in many ways that it is not a one-to-one relationship, and there's things that can affect the amount of chlorophyll A in the water that don't necessarily change the amount of biomass of phytoplankton. But it is a common index, and we know some of the warts. And because of its commonness, it's used in many, many monitoring programs. So we compare it across time. So now that we have our metrics and how we're going to measure this, we went about looking for different time series in many lakes in order to ask this question, are blooms getting worse? But we needed to have some requirements for what those time series would look like, right? And so one of the first things is, well, how frequently do you need to measure chlorophyll in a lake in order to capture the change in magnitude, severity, and duration? And so what we used were over 30 lake years of high frequency data from various lakes across the Midwest where there were sensors in the water taking measurements. You're seeing one example here from Swan Lake. This data was collected by David Ortiz, who was a master's student in my lab. And you can see these nice bloom that occurred in June and July in Swan Lake. And then the green dots are where the Iowa Ambient Lake Monitoring Program, which we'll talk a bit more about in a bit, where that Iowa Ambient Lake Monitoring Program went out and visited Swan Lake 3 times during the summer and was taking measurements. So how well can you define magnitude, severity, and duration if you have 3 measurements in a summer versus 100 measurements from every single day? So we did this rarefaction analysis to figure that out across these 30 lake years of data and found that you need on average 14 days to capture these bloom metrics. So a measurement every 14 days or 2 weeks. And then next, we didn't want to have just look at the change over a couple of years. As we all know, particularly as the climate is getting more and more variable, you can have a couple of years that are quite anomalous versus others. We wanted to look at longer term trends. And so we required that 10 years of data minimum of summertime chlorophyll measurements every 14 days was a requirement for a time series to be included in our analysis. And finally, there had to be minimal gaps. We didn't just want one summer of data in 2002 and one summer in 2020 and to draw a line through those. So there needed to be only 1 year of data missing from that time series in the gap. And so we used the Lagos database, or the Lake Multiscale Geospatial and Temporal Database that was created by Pat Serrano and colleagues, just a huge team and a massive resource for our community in understanding lakes. And through that, we found 323 lakes that met our time series criteria of at least 10 years of data, no large data gaps, and had chlorophyll measurements during the summer of every 14 days. And so we were able to use these, what we started referring to as unicorn time series. They're pretty hard to find, actually, these 323 lakes, to ask our question, all right, are algal blooms getting worse? And to do that, we used a generalized least squares regression of chlorophyll against time. And our model error had a first order autoregressive correlation structure. And that was just to control for temporal autocorrelation in these data. They are time series. And so what we found, we're looking here at the three different metrics, change in magnitude, severity, and duration. And what's on the x-axis here is that standardized trend coefficient. So a positive value means an increasing trend in that metric, negative being the opposite, and they're histograms. And so a key thing to take away just from here looking at this is these are not highly skewed distributions. They are not skewed all the way to the right, which would we expect if there was this widespread intensification of algal blooms. Instead, they're pretty normally distributed and centered near or around 0. And so this is our first piece of evidence that there's no widespread intensification of algal blooms in the recent period in these 323 lakes. And in fact, these are all the standardized trend coefficients, but if we were to just look at which trends were significant at an alpha of 0.05, we found that 11% of lakes in this data set were getting significantly worse in one or more of these metrics. However, and quite surprising to us, 17% of the lakes were getting significantly better in one or more of the metrics. And in fact, the lakes that were getting better, 2/3 of them had at least 2 metrics in which they were had a decreasing significant trend. So this was really surprising to us. Of course, it ran counter to the hypothesis that we'd started with in expecting there to be widespread intensification, and in fact found that wasn't the case, and perhaps a few more lakes are getting better as opposed to worse, at least in our data set. And so I think as a scientist, when you have that really surprising result, you want to go to your colleagues, go to the literature, and try to understand whether what you're seeing is really anomalous, or if there's folks that are looking at this question perhaps at slightly different angles and finding similar evidence. And so in doing that, what we found is that there's actually this mounting evidence that algal bloom intensification, at least in the recent period, may not be as widespread as perhaps we would expect based upon the way that the globe is changing. So for example, Sam Oliver and colleagues found that over 2,900 lakes had the majority of those lakes had no trends in chlorophyll concentrations since the 1990s. Taking a very different approach, Simon Topp and colleagues used remote sensing, looking at 1,400 lakes across the United States, and found that on average, for the majority of lakes, water clarity was slightly improving and not declining. Now, water clarity is influenced by many things, but one of those can definitely be blooms, and so that's a component. And then in another remote sensing study done by Ben Kramer and colleagues found that chlorophyll decreased across 56% of pixels. And this was in a set of over 300 globally distributed lakes. Then that time period was from 1997 to 2020. So perhaps there is some mounting evidence that during this period where we've seen rapid change in global drivers, we're not seeing the same sort of change happening in all lakes widespread. Some lakes are getting worse, some are getting better, many are not changing. But as I said, we did see variability, right? So you might be sitting there thinking, well, Grace, my lake has been getting worse, right? This is definitely something that's happening. And that's definitely true. There are many lakes, like the one that's right outside my window here, Lake Mendota, where if we look at the trends in Lake Mendota, the magnitude and duration of blooms has been significantly increasing. Whereas Monona, right next door, just across the isthmus, has not seen any significant changes in magnitude, severity, or duration. And so lake to lake differences in bloom trends we're observing with lakes right next door to each other. And in addition to that, if we look regionally, so for example, move from southern Wisconsin up to northern Wisconsin, where our North Temperate Lakes long-term ecological program is, we have over 40 years of data on those lakes. We see that some lakes like Aliquash are significantly decreasing in their bloom severity and duration. So these lake to lake and regional differences were something we wanted to investigate more, and asking what's driving the differences in these bloom trends among lakes. And so we used mixed effects models where we had the predictor variables that you see here in these broad 5 categories as fixed main effects, and consider all two-way interactions with chlorophyll A. And we used EPA ecoregions as a random effect on the intercept to look at regionality. And long story short, out of those models, we really didn't find any support for variability being explained by land-lake connectivity or having to do with air temperatures or changes in air temperature. What we did find is that lake surface area as well as nutrient concentration made a difference, but the one part of the model that I want to focus on today, just for the sake of time, was this interaction between trophic state and trends in extreme precipitation. So what we found was that the trend in bloom magnitude is susceptible to changes in extreme precipitation, and that's particularly true in really eutrophic lakes, so lakes that have a high mean chlorophyll A, like you're seeing on the x-axis here. So the greener lakes, or those with that high mean chlorophyll A, are also that are experiencing an increase in extreme precipitation, are more likely to have an increasing trend in bloom magnitude. But green lakes that are experiencing a decline in extreme precipitation over the period that they were studied have a strong declining trend in bloom magnitude. And I think this is particularly interesting because it's these really green lakes that tend to be the focus of our management and our restoration activities, because they have the biggest potential threat to human health and ecosystem services. And so thinking about this interaction of these lakes with the extreme precipitation, it's possible that the effect of nutrient management efforts is being magnified in watersheds that are experiencing less intense precipitation. So where precipitation is declining, that's helping out any perhaps management or restoration that's occurring there, contributing to that strong negative trend in magnitude. But extreme precipitation that's increasing might be overcoming and potentially reversed in watersheds that are seeing this extreme precipitation. And so in order to combat the effects of extreme precipitation, management actions might focus on mitigating nutrient runoff and erosion. So really thinking about these extreme precipitation events tend to be very high energy runoff events. So really focusing management on erosion and nutrient runoff for those high energy flows, as well as thinking in lake about how those high energy flows and events that often come along with high winds and such might be influencing stratification. So ways to enhance stratification and decreasing sediment resuspension could be ways in order to try to address in lakes that are experiencing increases in extreme precipitation. But our current management strategies, our restoration strategies that we're using in these eutrophic lakes, if they are experiencing these intense precipitations, may just be essentially running to stay in place. And so we need to continue to think about new tools and strategies as we look forward to adapt to the changing climate and how we're managing our lakes. Now, one of the questions that I often get when I present that story about long-term trends is, well, what about cyanotoxins, right? We were just looking at biomass of phytoplankton, but what about cyanotoxins, and are they getting worse? And I wish that that was a question that I had the ability to answer right now. There are lots of really great long-term microcystin monitoring data sets out there. They're not collated in a way like we were able to find the chlorophyll data. And so that's still work that we're undertaking and interested in doing and trying to understand how those microcystin trends have changed. But one thing that we do have is microcystin monitoring that tends to occur, for example, in large-scale lake surveys. So trying to understand where is microcystin across the landscape or even across a continent. And then we use those data to build statistical models to understand what characteristics are accompany a toxic lake or lake that has high microcystin, so that we can use that to inform our monitoring and management. And so for this next section, we're really interested in understanding, can we use those lake survey or snapshot survey data to build models that are useful to be applied in the future? And one of the reasons why this can be so tricky is because variability in both microcystin toxin production and cycling among lakes and among years is just quite challenging, because the microcystin cycle itself is quite complicated. And so what I'm showing here is some work that we recently published that's showing all of the pools, fluxes, and fates of microcystin within freshwater environments. And as you can see, this is an effort of a meta-analysis and synthesis of the information that we could find about what we know of how microcystin moves across these various pools. And in particular, I think it's complicated to make these predictions, especially when surface waters are connected to other surface waters that might have toxin production. And so we're dealing with import and export from those systems and trying to predict and understand that, as well as if there's strong interaction between the sediments in the water column and the way that that microcystin is being stored or removed from the system. But we do need to monitor microcystin, right? Regular monitoring is a really important tool that we have for protecting public health, but it is a resource-intensive and time-intensive process, right? It's something that takes specialized equipment, can take a lot of person power, and can also take a lot of time between the time the sample is taken and when those results are available. And so there is a need to be able to streamline or make more efficient where we're allocating our resources in terms of toxin monitoring, so that it can have the most protection for public health. And so one strategy that's been taken is using comparative snapshot surveys. And by snapshot, I mean one or very few sampling events in a lake, perhaps within a given year. And using that information, measuring microcystin, measuring many other attributes of the ecosystem, the physical, chemical, and biological components, to characterize whether or not a lake is toxic using statistical models, whether that toxin is detected, and try to understand where that is. But those surveys are by nature not designed to capture necessarily the dynamics of harmful algal blooms and when toxins are being produced, particularly that really detailed microcystin cycle. They could also have taken place during a year where there's a very anomalous climate conditions that might be influencing which lakes are producing toxins. And they tend to be designed around environmental gradients so that we can really capture things like nutrient gradients in order to see a statistical signal, right? And so the question that we wanted to ask was, how well does a lake classification model that's built from a single year snapshot survey, how does it do in terms of performance of classifying lakes as having toxin detected and not detected? And how can we use it in future years to continue making those predictions if we have new data? And so to answer this question, I use the Iowa Ambient Lake Monitoring Program data set. So prior to my time here at Wisconsin, I was actually an assistant professor at Iowa State University from 2017 to 2020. And so as a part of that, I worked with the Iowa Department of Natural Resources to run this ambient lake monitoring program. This is 130 lakes that you see in the map here shown with their EPA ecoregions in the underlay. And for this program, we sampled these 130 lakes 3 times every summer. And that sampling included many water quality variables, physical, chemical, and biological parameters. And starting in 2017, when I started, we began collecting microcystin concentrations as well during those sampling events. So in addition to the microcystin, as I mentioned, many chemical variables, including nutrients, and biological variables such as phytoplankton and zooplankton. And so if we looked just at the microcystin data, toxin concentrations from those years of the program that I was involved, you can see what I'm showing here is total microcystin concentration as a summer average in each lake on the y-axis there. Note the log scale. And then rank order along the bottom. So from the lake with the lowest concentration to the highest. And so the way to read this in thinking about how many lakes had detectable microcystin is you see this flat line along the bottom. When the line starts to curve up, then we know the number of lakes that had detectable microcystin that year. So as you can see, for example, in 2021, only about 38% of lakes had detectable microcystin. Many of them were below detection at that limit. Versus in 2020, we had almost 56% of lakes had detectable microcystin. And so we used the 2017 data to start to build the statistical model to try to classify lakes as either toxic or non-toxic. And then we used that 2017 model and applied it forward to the 2018 through 2021 in order to see how it performed in different years. And when I mean different years, they were quite different. 2018, in fact, was a very wet summer. And in some parts of central Iowa, it was the second wettest summer on record. Versus in 2021, it was a very dry summer, and we actually had widespread drought across the state of Iowa. So really very different climate years than 2017 when the model was built. So to build this classification model, we used machine learning conditional inference trees. And so these conditional inference trees are a method for regression and classification. In other words, it's taking all the candidate variables that we provided, in this case it was 37, and using those to try to put lakes into the buckets of either microcystin detected or not detected. And then we can evaluate, based on the microcystin data we collected, how well the model did at classifying those lakes. And the reason for using conditional inference trees in this case is that they're capable of handling missing or censored data, and they handle correlated variables quite well. And we used a significance test to select the most important variables for the model. And so, as I said, we started with the 2017 data, all the physical, chemical, and biological parameters that we collected to build a model, and then we wanted to see if we could apply it forward. So starting with the 2017 data, what I'm showing you here are just the most important variables that the model identified for classifying a lake as having detectable microcystin or not having detectable microcystin. And as you can see here, they sort of fall into some various categories. Things like nutrients and productivity variables being very important. Then next, sort of the geographical context that lake is sitting in, its ecoregion, specific conductance, and then biological components of the lake, things like total zooplankton biomass. And the larger the bar, the greater the importance, or the higher the variable importance within the model. And so while we could pick apart each one of these variables in terms of how they relate to the probability of detecting microcystin, I just want to focus for the sake of time today on the top most important predictor, pH, and this really interesting threshold relationship. So it really surprised me to have pH be the most important variable for classifying whether a lake was going to have detectable versus non-detectable microcystin. And as you can see in this partial dependence plot here, the probability of microcystin detection has this really strong threshold relationship with pH, such that at lower pHs, the probability is lower. Then there's this sharp increase in probability between 8.4 and 8.6. And it's in this region, in fact, where we actually see CO2 concentrations going to zero, right? Thinking about the bicarbonate buffer system. And so bicarbonate is the inorganic carbon source that's largely available. Cyanobacteria are really good at using that. They have lots of mechanisms in order to harness and use that bicarbonate as their inorganic carbon source for photosynthesis. And so the way that I view this pH variable is that it's really an indicator of both productivity. You have to get these high pHs, you need to have a lot of photosynthesis happening. And so the bloom is going, it's growing, going like gangbusters. And the pH also being that high, meaning the CO2 isn't around, and so is preferentially creating conditions where cyanobacteria are thriving. And so that's perhaps why it's coming out as one of the most important variables for classifying whether a lake is going to have detectable microcystin. So that's what informed the model. How did the model itself perform? Well, if one way that we can evaluate that performance is using something the area under the curve, that's the receiver operator curve. And essentially what this allows us to do is say, how well did the model with these two buckets of detectable and non-detectable put lakes in the correct bucket? And if the area under the curve is 1, then that's a perfect model. Each lake ends up in its correct bucket. If it's 0.5, that means that the model did no better than random classification. It's just as though the lakes were thrown at the buckets and it was random. And so our minimal acceptable model level would be about 0.7. As you can see, the 2017 model here, which is being shown, is nearly perfect. It has an AUC of 0.97. So using the 2017 data, we were able to, the model classified lakes as detectable or non-detectable for microcystin very well. Well, what if we use that 2017 model and feed in the 2018 pH and nutrient data and such, and the 2019, how well does it perform? And so that's what you're seeing here. There was a decline in model performance, but still well above what we would say our minimum acceptable model is. And so this is, I think, quite interesting because it gives evidence that the classification model performance didn't substantially decline. It certainly did decline, but didn't substantially decline when applied forward in future years. And that was surprising because this model built on 2017 data was still informative in years that had very different climates, such as 2018 when it was wet and 2021 when it was very dry. Also, despite the fact that Iowa has widespread agricultural land use and is a really, really nutrient-rich area, in addition to many other places in the upper Midwest, we found that despite that widespread land use, it was really the degree of eutrophication, not just that's a green lake or a eutrophic lake, but how green or eutrophic it was, and what the dominant agricultural land use was, whether it was row crop agriculture or pasture, really were informative. So even a narrower environmental gradient, still really important. But this is just one lake or one state, one set of lakes in just these 5 years. And so I think it's important that we have similar investigations using other data sets similar to this in other regions to build further evidence on how useful these statistical models are in terms of classification would be for informing policy and management of how we monitor for microcystin and protect public health. So another way that we can think about protecting public health and monitoring for these toxins is thinking about whether or not we can predict a bloom before it's going to happen and warn people. And that's the last story I want to tell you this morning. And this is really tied to whether or not we can measure or in fact enhance resilience to try to prevent these blooms from happening. And so what I mean by prediction is, what if we could predict a bloom before we could see it? In other words, if we have this high frequency data, let's say these are daily chlorophyll values, over time, during this period in the blue box here, where chlorophyll values are low, people are enjoying all the ecosystem services that are provided by this ecosystem. What if we could use this variability in information to predict a bloom before it happens and warn people, or perhaps even intervene and mitigate it? So can we predict it, and is there enough time to do something? And the way to do this is really by thinking about algal blooms as a regime shift. And so the two states or regimes that lakes can be in is a clear water state. Now, if it's a shallow system, that could very likely be dominated by macrophytes or aquatic plants. Or if it's a deeper water lake, just clear water. But you can, versus the algal dominated system. So these blooms that we all focus our research on, right? And so there's a shift between the two, from this stable clear water phase to these stable cycles of algal blooms is the shift, a hop bifurcation. And if we think about the ecosystem being this ball here in these two states or the basins, this is probably a diagram that you're pretty familiar with. The height of the saddle, or the hump between these two basins representing the clear water and the algal dominated state, is the resilience of the system. So in this case, there is a pretty steep basin. It's a very high saddle there. And so this system has high resilience. This is under conditions of low nutrient loading. But of course, there's variability. There's stochastic factors that are occurring all the time that are pushing that ball around in that basin of the Clearwater state. So perhaps a storm comes, there's some nutrient loading, that's going to be energy that moves that ball around. But because the basin walls are high, we see that there's pretty low variance. The ball is going to come back to the middle pretty quickly, and there's low autocorrelation. But let's say there's land use change in that watershed, and over time, nutrient loading, ambient nutrient loading increases. So the resilience of the system is being lowered. And that same storm that comes along and adds nutrients, now that the basin is much more shallow, is going to push the ball around even farther in the basin. And so in this case, if we were to track, say, the chlorophyll concentration over time, we would expect to see that variance is increasing because the ball moves farther away from the center with each push. And autocorrelation, so how much does yesterday look like today, is also increasing. Now, eventually, resilience will be so low, or there's a big enough external shock from the system that it'll flip into that algal-dominated state. And that's particularly likely to happen when there's low resilience in the system. And so, as a part of a set of whole ecosystem experiments that we started about a decade ago, my collaborators and I were interested in understanding, are there statistical early warnings of these blooms occurring? In other words, can we use daily automated measurements of things like chlorophyll and phycocyanin to look for these increases in variance and increases in autocorrelation that should be characteristic of that regime shift to the bloom state about to occur? And we tested this, like I said, by doing a series of whole ecosystem experiments up in northern Wisconsin at the University of Notre Dame's Environmental Research Center. And so just briefly, the way that our experimental setup is that we had two lakes where we were adding nutrients. These were Peter and Tuesday lakes that you can see pictured here. And the idea in Peter and Tuesday lakes is we did daily nutrients additions of phosphorus and nitrogen. So we were adding this external nutrient loading to the system. And we were measuring every day using these high frequency sensors in the water. One of them is pictured there. To look for these statistical warnings of an impending bloom, a rise in variance, a rise in autocorrelation. And if we saw those early warnings, we continued to do the nutrient addition to see if in fact it was predicting a bloom occurring or just some other noise that we happen to be measuring in the system. And at the same time, we had a reference ecosystem. In ecosystem experiments, we don't refer to them as controls because you can't truly control an ecosystem, but it's our reference where we weren't adding nutrients, but we were still looking for those early warning signals with the expectation that we wouldn't see them and there wouldn't be a bloom. And so that was our experimental setup. And so no surprise, you add nutrients to a lake, you get a bloom. And you can see that in this picture of Peter and Paul lakes here, with Peter on the left in this lovely Dolichospermum bloom that's occurring. This was in 2015. And then on the right there is Paul Lake, where you're seeing the reflection of the clouds. It's otherwise crystal clear and blue. That's the lake that didn't have nutrients added to it. And we see that reflected in our daily chlorophyll data as well. So that's what you're seeing here, the reference Lake Paul in the blue line, where we weren't adding nutrients and we didn't see any changes in chlorophyll, versus Peter in the green line there. We did add nutrients and we see a lot of variability and then this big bloom happening towards the end of the summer. And these are data from 2014. So then the question is, well, were there early warning signals prior to this bloom in 2014? And so again, we were using rolling window statistical methods to look for a rise in variance and a rise in autocorrelation. And just to cut to the chase, we did this in these two lakes for 3 years, so from 2015 to 2015. So we have 6 lake years of experimentation. And how frequently did we see this rise in variance and rise in autocorrelation? Well, we saw these signals, these early warning statistical signals, in many of the lakes. In 2013, in Peter Lake, we actually didn't end up getting a bloom. I'll talk about that a bit more in a minute here. But as you can see, the number of days before a bloom occurred, so bloom conditions were reached, we had those early warning signals firing off anywhere between 6 to 57 days beforehand, so almost 2 months. So in some cases, a lot of warning, and in some cases, very little warning. Interestingly, though, the more severe the bloom was, so for example, that bloom in Tuesday Lake in 2015, it hit almost 80 micrograms per liter of chlorophyll. The number of alarms that went off prior to that was proportional. So the more severe the bloom, the more alarms that went off. So perhaps the more confidence we could have in the fact that we are going to be seeing this bloom occurring. But these are really simplified systems in a way. They're experimental lakes. They're true and real lakes, but they're ones that we've worked on for a very long time, and we have a pretty good idea of how they're going to behave. And they are pretty much dominated by their pelagic zones. And that's not the case for a lot of lakes, especially lakes that are susceptible to harmful algal blooms. Right. So just as an example, this is Swan Lake in Iowa again. So that same lake before that I mentioned that David Ortiz had been studying, you can see pictured there. Swan is this wonderful nutrient-rich natural lake in Iowa, and it has a nice shallow lake. You can see a lot of the macrophyte beds that are being shown here, the American lotus, the sago pondweed, and just the amount of variability that we see across this lake. And so what I've plotted here, David went out actually to 98 stations across the lake every week and measured things like phycocyanin concentration using sensors. And you can see that variability over time. I'm showing 5 of those weeks here, as well as spatially across the lake. And so how well does our fixed station that's sitting at one of those points do in terms of actually measuring these things? And can we actually pick up some of these early warning signals in these very real world and messy systems? And so what David actually did is he looked for those early warning indicators using these real world systems. So 5 lakes in Iowa, or 4 lakes in Iowa, and 5 years of data. You can see those listed here. And these are lakes that are eutrophic and consistently experience harmful algal blooms, many of them toxic. And we see what he found was that prior to bloom conditions, the onset of bloom conditions, he saw those early warning statistics firing off 17 days beforehand on average. And before the peak or the worst part of the bloom, 51 days beforehand, he saw those early warnings, the rise in variance and rise in autocorrelation firing off, even in these very messy and very spatially heterogeneous ecosystems. So this makes us think, well, what is the potential of using a tool like this, such as early warning indicators, to be proactive and protecting ecosystem services? Does it have that potential? And, you know, perhaps, maybe, if you had sensors in the water, you were doing real-time analysis, you being able to have these early warning signals combined with your own intuition about that ecosystem and how it's behaving and looking at things like weather reports might give you confidence in doing actions to intervene to protect things like drinking water and irrigation water supplies, switching those supplies, posting signs, starting microcystin monitoring on the beaches, protecting recreational users and such. And so there's lots of actions that could be taken. But it's not a perfect tool and it takes some skill to use, right? So that's pretty difficult. And there's really one thing about these early warning indicators is they are feeling around the edges of resilience. We're inferring that resilience is declining because there's the rise in variance and the rise in autocorrelation. But it's not actually a direct measure of resilience. And so as a part of a team recently funded by the National Science Foundation, we're going to be embarking on a new set of whole ecosystem experiments where we're going to be really asking 2 questions. And again, we'll be using Peter, Paul, and Tuesday Lakes to understand, first, can we reliably measure and compare resilience among ecosystems and within the same ecosystem among years? And so under Steve Carpenter's leadership, we've been working to develop a number of different tools for actually measuring resilience. Some of them you see here, they're things like ecosystem models, dynamic indicators like the early warning indicators, as well as other dynamic indicators using that time series of data, as well as stochastic indicators. So new methods like mean exit time, which actually allow us to measure stochastic resilience as originally proposed and envisioned by Halling back in the 70s. And so that's the first goal. Can we actually reliably measure and compare resilience among lakes and among years? Because if we want to have any hope of actually, say, intervening and enhancing resilience in a system, we need to actually know that our interventions are doing something and be able to measure it. And enhancing resilience is one of the best adaptive management strategies we have in terms of going forward and protecting these ecosystem services in these lakes. We also want to know and test if we can measure resilience, can we intentionally modify resilience and measure the effect on its susceptibility to nutrient loading. In other words, can we measure the effect that enhancing resilience would have in this lake on algal bloom susceptibility to external nutrient loading? And so in order to do that, we actually were thinking a lot about our previous whole lake nutrient addition experiments. And I mentioned briefly that in Peter Lake in 2013, we didn't have an algal bloom. We added nutrients, but we didn't see a bloom. Now, we were adding nutrients at a pretty low concentration, but also coincident with that, we had one of the darkest watercolor years in our over 40-year record of what's been happening in Peter Lake. In other words, there was a lot of terrestrial organic matter, dissolved organic carbon that was coming in from the watershed that year, and Peter Lake looked like a cup of coffee, a really weak cup of coffee, but it was very dark. And so the light climate was much different than in other years, and we think that contributed to the fact that despite the fact we added nutrients, there wasn't a bloom. And so for this experiment, we will be adding, in addition to adding nutrients to these lakes, Tuesday Lake is a much more organic matter rich, low transparency lake. We'll also be adding aquashade to Peter Lake in the second year. And the goal there, aquashade is perhaps a tool that you use as well in some of your own management of systems, but our goal there is to try to increase the amount of light attenuation, so acting like that dissolved organic carbon, but without adding the nutrients that tends to come along with dissolved organic matter, in an effort to enhance the resilience to the same level of external nutrient loading. And so stay tuned for the results of that. We really look forward to being able to dig into whether or not we can modify and measure resilience and modify resilience. And I just also want to give a very quick plug that we'll be embarking on this next summer, and we have a master's position available here at the Center for Limnology in support of this work if you know of anyone that might be interested. So through the research that I've presented today, while we didn't see for long-term trends, for example, that algal bloom intensification is not currently widespread, and we do have some tools such as monitoring and statistical tools in order to evaluate and mitigate these things, we know conditions are going to continue to change. Eutrophication is going to continue to accelerate in some regions. Precipitation is going to continue to intensify, and we need management tools to protect our health and human health and resources, things like microsystem monitoring and applying those statistical tools, as well as managing and measuring resilience. But in order to protect our lakes, we need to continue to reduce eutrophication, promote restoration, and continue to build these tools to better adaptively manage our inland waters in the face of a changing world. And with that, I'll just leave it on the acknowledgement slide, thanking our funders and my collaborators, and I'm happy to take your questions.
Fabulous. Thank you so much for the presentation, Grace, and sharing your research with us. We do have a lot of questions that have come in, and we do have a hard stop of noon today. So we've got 7 minutes to get to as many questions as we can, and we will, maybe you can reach out to Grace via email if we don't get to all the questions. So I'll quit talking and start asking questions, and we'll try to get through these. So a lot of people were asking, were wondering what early warning sign signal parameters you used.
Yeah, so we were looking for that rise in variance and rise in autocorrelation in chlorophyll. So chlorophyll and phycocyanin, which are pigments for those phytoplankton, in particular the phycocyanin for cyanobacteria. Dissolved oxygen, which is going to change depending on the amount of photosynthesis. So if a bloom is really ramping up, we'd expect that to increase. And pH, because of that same reason, as I mentioned before, with the pH changing with the amount of photosynthesis in the water. So those were the four variables.
Great, thank you. We also had a question early on when you were talking about how you were selecting your lakes and wondering if there is a bias in what lakes meet the requirement for sampling frequency. For example, are those lakes sampled that frequently for chlorophyll because they are known to have a problem?
Yeah, that is an excellent question and one we have definitely grappled with. I'm so glad that was asked. And so we did do some work to try to understand if the the rate at which things were being measured, how long they had been measured, as well as if we could find evidence of whether or not there had been restoration in that lake was associated with whether or not we saw a positive or a negative trend in chlorophyll. But fundamentally, we are just using found data. And so that's where I think studies like Simon Tops, where they're using remote sensing to get at the same sort of questions and seeing similar trends in water clarity, help provide that evidence that even if our data set is biased, the remote sensing is not biased in the same way. And so that's that weight of evidence building towards, but we certainly cannot get around that potential bias.
Thank you for that. Another question that several people have, wondering about HABs management. Is it possible that HABs don't look like they are intensifying because people are managing the lakes better in response to HABs?
Yeah, that is certainly possible. And so one thing that we tried to do was for the long-term trends, for all the lakes where we found significant decline, we picked through all the local reports that we could find, and local news media reports, because if a lake group is doing a restoration and putting a lot of money into it, they're probably going to put a press release out. And so what we found is that 65% of the lakes that had significant declines in one of the bloom metrics had had some form of restoration occurring on it during the period that it was studied. And so it's certainly possible that we are seeing part of that management show up in the data set, that water management, but that's a harder thing to really pick apart. So we're still working on that to do that in a quantitative way and not just an ad hoc sort of way as we have.
Okay, thank you. Next is for your long-term trend study. Did you see any differences in trends for impoundments and reservoirs versus natural lakes?
Yeah, great question. We did look at that in our statistical analysis, and it didn't come up as a significant variable. But I wonder if part of that too is we might not have a robust enough sample size. And so I could definitely see a lot of arguments about why you might see different trends in those two different types of water bodies. It didn't come up in our analysis, but I don't think that means it's because it's not the case. I think we need to do some more looking.
Okay. Are you aware of technology that can mitigate algal blooms and the associated toxins?
Yeah. So there are a number of technologies that are out there. A lot of them are, of course, the number one way in mitigation is controlling nutrient inputs, right? And that's a long-term, there's a lot of legacy nutrient on the landscape as well as within the lakes. So that's going to a long-term multi-decadal solution. But during that time, there's other things. Aquashade is sometimes used, for example, like we're going to use in our experiment, is sometimes used to limit light and algal growth. There are, in some regions of the world and even some US states, things like copper sulfate are used, as well as there's other technologies that are out there as well. And I think they all have their pros and cons. And one thing particularly of note is thinking about application and the size of the system that you're trying to apply them to. So that's almost a whole nother talk in itself. But there are lots of tools in the toolbox.
Great, thank you. Have you ever examined the influence of invasive species?
Oh, yes, absolutely. So in that particular study, the 323 lakes, we were not able to bring in invasive species information. It's something that we're actually trying to get funding to do because we think they could play a pretty big role. And for example, here in Lake Mendota, right outside my window, we know that with the invasion of Bythotrephes, the spiny water flea, that we've seen lots of changes in when blooms are happening, how long they're happening for, and their toxicity. So that's something I hope to dive into more because I think it could play a really big role.
Very good. A couple people were wondering about the regime shift. What is the time horizon? Is it daily, seasonally?
As in terms, perhaps there's no more clarification in the question. So the regime shift itself, you can witness that shift or have the threshold be crossed from the clear water state to the algal dominated cycling state within a season. That there can also be the cross back to the other in the other direction. That can, in these lakes, because of the way nutrients flow and the residence time happens on about an annual basis with the nutrients that we add. In some systems, like the inertia that's in Lake Mendota, for example, is pretty much in that state all the time. But that regime shift or that threshold crossing is something that happens in most lakes on a sub-annual basis. So you can witness it multiple times, and that actually helps us measure the resilience and map the landscape, the stability landscape of the system.
Okay. Well, Grace, thank you again. We are out of time. We did have questions that we didn't get to, so you'll see her email in the chat box if you want to reach out. And thank you to everybody for participating, and thank you for your presentation today. It generated a lot of questions and interest, so well done.
Wonderful. Thank you so much. Thank you all for your time.